Dear students, it was initially thought that the Earth is revolving in a circular orbit, but few of the calculations and data is not fitted in this concept. So Kepler's find out and figure out that the uh, datas and calculations were best fitted when it is uh, put in case of ellipse. Okay, elliptical path. So first of all, what is ellipse? Ellipse is an oval shape uh, figure in which there is a two focal point or two focus. For example, there is one center in the circular path or in a circle. Similarly, in ellipse there are two focal point or focus and two axes, that is the short radius of the elliptical orbit or ellipse is known as semi-minor axis, and the uh, longest radius of the ellipse is called semi-major axis. So on the basis of this figure ellipse, Kepler postulated the first law of orbit. The law states that each planet moves in an elliptical orbit or elliptical path with the Sun at one of its foci, one of the focus. The planet revolves around the Sun, and position of Sun is at one of the focus. The second law he postulated as the law of areas. The speed of the planet varies in such a way that the radius vector drawn from Sun to a planet sweeps out equal areas in equal time. So we uh, may think that the ellipse is an oval shape, and when Sun is situated at one of its focus, then how the area of the uh, area swept out is equal in equal interval of time. So here we can see that there is a time at which planet comes near the Sun, and at one of the end planet go at planet is at maximum position or separation from the Sun. So when the Sun is at a shortest distance from the Sun, the radius vector is short, and in that case the speed of the planet becomes greater, or speed increases at that condition. And when the planet is at a largest distance from the Sun, the radius vector become longest, and at that time the time taken by the planet to cover small distance is small. That means the in equal interval of time the area or the distance covered by the planet is small at largest distance. So we can say that when planet come near the Sun, the speed of the planet increases, and when it goes away from the Sun or is at a largest distance, then the speed of the planet decreases, due to which displacement is small, and the product of area of the triangle traversed by the uh, planet area of the triangle traverses by the planet in time t is equal to that the area covered by the planet when the position of the planet is near the Sun. Therefore, we can say that the area of the area swept out by the planet is equal in equal interval of time. In the second law, we come to know that the planet moves with variable speeds. That means the speed or velocity of the planet changes throughout the orbit. So when planet is near the sun, the kinetic energy is maximum, and when it is away from the sun, kinetic energy value attains minimum value. So in this orbit, the total energy of the planet remains constant. Kepler postulated the third law as the law of periods. That is, the square of the time period of revolution of a planet around the sun is directly proportional to the cube of the semi-major axis of its elliptical orbit. That means at which the planet orbit is t squared is directly proportional to the r cube of r. That is, r is the length of the semi-major axis. Since different planets are at different distances from the sun, therefore their time periods are different. So we can write the ratio of t squared directly proportional to r cube as like this. So the third law is expressed as like this: square of time period of revolution of any planet in an orbit is directly proportional to the cube of the length of the semi-major axis. So let T1 and T2 be the periods of revolution of any two planets around the sun, and R1 and R2 be the length of their respective semi-major axes. Then the ratio can be written as like this. So it is in accordance with the Kepler's third law of motion. So this type of relation we have obtained during the derivation of time period for a satellite. Since the different planets are at different distances from the sun, therefore their time periods are different. Uh, the period of revolution of Mercury, which is closest to the sun, is 81 days, and Earth is separated by distance greater than the Mercury. Therefore, the period of one revolution is equal to 365 days.